Today's notes are on limits algebraically. It's fairly easy to look at a graph and determine if the left side and the right side are approaching the same y value, but when you're looking at a function, it's not so easy. We do have some strategies though. First step, always just try substitution. If you plug in the value that x is approaching in for x, and it gives you a defined value, then that's it. If it doesn't, then we can factor, simplify, multiply by a conjugate to see if it produces a defined value. And the last thing, if we're looking at a piecewise function, we're going to look at both sides of the limit value. So we'll have to plug into both pieces to see if the both sides equal the same y value. If that's the case, then the limit exists. So let's take a look at some of these algebraic examples. Number 1, as x approaches -3, let me change my ink, there we go. The limit as x approaches -3, we can see in the denominator that's going to give you 0. In the numerator, if I sub in a -3, that's going to give me 9 minus 3 minus 6 is 0. And this is what we call our indeterminate form, which has no numeric value. So we've got to factor and see if we can cancel a common factor. So as the limit as x approaches -3, the numerator factor is x plus 3, x minus 2. And we can see that we have a common factor. Remember, that produces a hole in our graph. So then my reduced function is just x minus 2. At this point, if I substitute in -3, that's going to give me -5. Let's take a look at the next one. Again, if I sub in for the denominator, that's going to give me 0. In the numerator, though, that's going to give me 9 plus 3 minus 6. And so that's 6 over 0. That's an undefined value. And so if you think about, we've got a rational function, and the zeros of the denominator create vertical asymptotes. So we can say that we have a vertical asymptote at x is equal to -3. Vertical asymptote is where the ends of the graph are going to be approaching positive or negative infinity. And if that's the case, that's not a defined number. Does not exist. The limit does not exist. In the third example, when we plug in -3, the denominator is going to give me -6. The numerator will give me, let's see, -3 squared is 9 plus 3 minus 6. So that's 12 minus 6 is 6 over -6. So the limit as x approaches -3 is -1. And one more example, the limit as x approaches -3, the denominator is going to give me -6. In my numerator, -3 squared is going to give me 9 minus 3 minus 6, so that gives you 0 over -6, which is the limit as x approaches -3 is equal to 0. So let's look at some of these graphs. Now you are going to have to work these without a calculator, but just to see kind of what they look like. And in problem number 1, the limit was equal to -5. Let me show you the graph of number 1. That's going to be right here. Let's see if I can expand this. Okay, so when we're looking at this graph, as x approaches -3, which is right here, our y values are approaching -5. Now remember, we said that that was a hole, and that's exactly how it's showing up on the table. But when you have just like a linear function like this, it's just that one instance, so it's not going to show up. Okay, let's take a look at the second one. We said the limit as x approached -3 did not exist because we had a vertical asymptote. Here is the graph of the second problem. And we can see that at an x value of -3 right here, we do have a vertical asymptote that would just come straight through here. Okay? All right, in the next problem, we said the limit as x approached -3 was -1. And and -3, -1. That's a point that's defined on the graph. And there it is. And in our last problem, we said the limit equaled 0. The y value equaled 0, and so let's take a look at that one. And there it is. It is the x-intercept on the graph. All right, let's take a look at two piecewise examples. So determine the limit as x approached 4. So we have a piece on the piecewise function to the left of 4 and to the right of 4. And as long as these give us the same y value, then our limit exists. So let's evaluate. F of 4 from the left would give you 2 times 4 plus 3, which is 11. And f of 4 from the right would give you 5 times 4, 20 minus 9, which is 11. So the limit as x approached 4 of f of x is equal to 11. Now let's take a look at the next example. So we're looking for the limit as x approached 0 of this function. So f of 0 from the left is 4, and f of 0 from the right is 0. So the limit as x approached 0 of this function does not exist. Okay, we're going to skip down to some other algebraic problems. We're going to cover some of these in my next video, but here are some other algebraic problems that I wanted to review. Okay, so this first one, limit as x approached 2 of 4x squared minus 5x plus 3. Let's just try direct substitution. If I plug in 2, I'm going to have the limit as 4 times 2 squared, so 2 squared is 4, times 4 is 16, minus 5 times 2 is 10, plus 3, so 19 minus 10 is equal to 9. All right, let's take a look at the next one. Again, I'm just going to start with direct substitution, see where it takes me. So I have the limit as x approaches 0 of 0 squared plus 4, that's just 2. Okay. The next problem, if I plug in a -6, let's see what happens. The limit x approaches -6. Well, in the numerator, I can see that's 0. And the denominator, -6 squared is 36 plus a -18 minus 18. Okay, it gives me the indeterminate form. So let's go ahead and factor. So the limit as x approached -6. The numerator is just x plus 6. The denominator, let's see, two numbers that multiply to get -18 and add to get 3. X plus 6, x minus 3. That multiplies to get a -18, and it adds to get a positive 3. I can see I have a common factor of the x plus 6. That means I have a whole or removable discontinuity at an x value of -6. So what's the y value though? After I cancel that common factor, I can direct substitute, because this is what I'm left with. So when I plug in -6, 1 over -6 minus 3 is -1/9. All right, my next problem, this is the sum of cubes in the numerator. And I happen to have those two sum and difference of cubes right up here. And so you probably want to write those down if you're not super familiar with them. You're not going to be given any formulas, so you might want to maybe add those to your flashcards or something just to practice. So what I do is I'm going to take the cube root of x cubed, and I know the cube root is 3. Wow, not 3. How about x? And the cube root of 8 is 2. That's going to be your a and your b terms. And so I'm going to go ahead and, because I know already I'm not going to be able to sub in a -2, the denominator becomes 0, the numerator becomes 0, I have the indeterminate form. So I'm going to go ahead and just jump to the next step. So the limit as x approaches -2. My numerator is going to factor to, let's see, x plus 2. I believe that, and that's all over x plus 2. I see right away I've got that common factor. Let's cancel that. Now we can try direct substitution. So this is the limit as x approaches negative 2. And if I plug in negative 2, that's going to give me negative 2 squared is going to give me 4. Let's see, plus 4 plus 4, how about 12? In the next problem, I can't plug in a 0 because I can see right away 0 in the denominator, and this will give me 1 minus 1, 0, so that's the indeterminate form. This problem, I need to multiply by the conjugate, and the conjugate is the binomial, or the term with the radical, but with the opposite sign. And so in this case, we're subtracting, so if I multiply by the square root of x plus 1, that should help to clean up this function. Okay, so let's see. I'm going to have the limit as x approaches 0 of x plus 1 minus 1 times, and I'm going to multiply by the conjugate, x plus 1 plus 1. Okay, so in my numerator, and I'm just going to FOIL these together, when I multiply the square root of x plus 1 times the square root of x plus 1, you're essentially squaring the square root, and so you're going to just be left with x plus 1. Okay, so then I'm going to distribute the square root of x plus 1 times 1. That gives me the positive square root of x plus 1, and then I multiply negative 1 times the square root of x plus 1. That's going to give me the negative x square root of x plus 1. So those terms cancel. So then I need to multiply the negative 1 times 1, and that gives me negative 1. All right, so now in the denominator, I've got x times this quantity. Okay, so now in my numerator, I'm going to go ahead and clean up just a little bit. See this plus 1 and this minus 1? And I don't need the parentheses really, because I'm just I'm adding or subtracting, so those 1's cancel. So all I have left in the numerator is x. Now I'm going to cancel that x with the x in the denominator. And so what I've got now is the limit as x approaches 0 of 1 over square root of x plus 1 plus 1. Now when I do direct substitution, I end up with, well, the 1 is in the numerator, and if I plug in 0 in the denominator, I have the square root of 1 plus 1, which is 2. And so that limit is equal to 1/2. Okay, 2 more. In this next problem, again, if I do direct substitution, I've got the indeterminate form. So let's go ahead and let's work out this binomial. So I've got the x minus 5 times x minus 5, and that's going to give me x squared minus 10x plus 25. I can see right away that my 25s are going to cancel. And so I've got the limit. Oh, and also let's go ahead and factor an x from the numerator. That'll cancel with the x from the denominator. So really what I'm looking at is the limit as x approaches 0 of x minus 10. Now if I do direct substitution,